Welcome back. We've now discussed the various components of a satellite's payload, and in this segment, we'll put them together and shake them. So each of the individual systems on a satellite are often built separately. The solar panels and electrical system, the communications equipment for receiving or transmitting data back to Earth, any of the cameras or other components, these can be built either in different labs or by different companies and often in different countries. These components are then integrated together in a quiet, clean room. The completed satellite is then shoved into a launch vehicle, forcibly lifted off the Earth, where it can feel like extreme accelerations and vibrations. The satellite is then released into the vacuum of space and expected to unfurl its solar panels and start working perfectly in that harsh orbital environment. It's actually pretty incredible that stuff in space works at all. And when something seems incredible, that usually means that there is a huge amount of work going on behind the scenes. And in this case, that work is in testing and retesting a satellite's payload. Each individual component of a satellite is often tested separately, and the tests are repeated as components are added together until the whole satellite is put together and tested yet again. The goal is to simulate the full sequence of launch and deployment into space. And this is critical because for 99.9% of satellites, once it's launched into orbit, there's no way to go back and fix or repair something. This process of testing will be different depending on where a satellite is headed and its planned lifetime. So for example, the testing process for a small CubeSat going to low Earth orbit for a few months will be much less extensive and less expensive as compared to a GPS satellite heading to medium Earth orbit with a design lifetime of 20 years. There are many different tests that a satellite undergoes to make sure it's ready for space. We're going to focus on two generic types. So first, our tests to make sure a satellite can successfully operate in the vacuum of space and handle the extreme temperature ranges that are expected. These tests are done in what's called a thermal vacuum chamber. This is testing the satellite's performance when it's in the space environment. And as the name suggests, there are two things going on here. The vacuum part means that all of the atmosphere is sucked out of this chamber, and the thermal part means that making sure the satellite components can operate over the range of temperatures a satellite is expected to encounter. And these two things, the thermal part and the vacuum part, are actually very much connected. This is because air acts as an insulator. The temperature of a satellite will behave very differently in air versus in vacuum. In thinking about the temperatures a satellite might encounter, you might guess that things are like super hot during launch and then get super cold once in orbit. And it's true that during launch, things can get pretty warm, but the payload is protected inside of the rocket from the worst of that. Once in orbit, though, the temperature can fluctuate between extremely cold and extremely hot. And this seems odd, like space should just be super cold, right? Well, it's true if you're out in deep space. As for satellites orbiting Earth, it's extremely cold when the satellite isn't in the sun, that is, if it's in the shadow of the Earth. Temperatures can get down to like 150 or minus 200 degrees Celsius, which is like way below freezing. But if a spacecraft is in the sun, it's actually absorbing heat. And depending on the type of material and the surface area of a satellite, the satellite can actually heat up to extremely hot temperatures, 50 to 100 degrees Celsius, and that's like the boiling point of water. For a low Earth orbit satellite with an orbital period of 90 minutes, a satellite is going in and out of the Earth's shadow and can have extreme temperature fluctuations every single orbit. Electronics do not like large temperature fluctuations. Imagine putting your cell phone first in a sauna and then in a blast freezer. Again, I wouldn't recommend it, but you can be sure that the electronics won't be very happy. In addition, like the cell phone case might get brittle and crack as the temperature changes dramatically from super hot to super cold. In designing a satellite, the materials and the electronics need to take this into account, these extreme temperature variations. And you can test these design decisions by placing either individual components or the whole darn satellite into a thermal vacuum chamber. Thermal vacuum chambers come in many sizes. There are chambers that are like the size of a refrigerator to do your testing of things like small CubeSats or individual components of a larger satellite. And there are thermal vacuum chambers the size of a house for testing large completed satellites. So this is a video of a NASA telescope being placed into a massive thermal vacuum chamber. The satellite is put in the chamber, the door is sealed, and then the atmosphere is slowly pumped out of the chamber, often over the course of a week or more. Inside of the chamber, there will be an energy source to mimic the radiation coming from the sun to test how well the satellite performs at different temperatures. Sometimes satellites don't pass these tests, and when this happens, a component is redesigned or rebuilt and the test is run again. The second kind of testing that satellites go through is to mimic the vibrations felt during launch. For vibration testing, a satellite is placed on a table that literally shakes it in all three directions. The strength and the frequency of that shaking is exactly matched to the rocket that a satellite will be launched on. So like for a satellite being launched on a Falcon 9, it'll be shaken differently than a satellite going up on a Falcon Heavy. The idea here is that nothing should break or come loose during testing. That is, both the mechanical connections like bolts or screws, but also the electrical connections should not come loose. So imagine working for months on an incredibly delicate piece of electronics for a satellite, and then placing it on a shake table and pushing the Frappuccino button. So here's a video of a satellite component undergoing vibration testing. In this case, it's a communications antenna being tested for a European mission called JUICE, which will study the moons of Jupiter. So the antenna is on a shake table that changes the strength and frequency of vibrations to mimic what's expected during the launch, in this case on an Ariane 5 rocket. The shaking starts off fairly gentle and then starts to get pretty intense for a bit. Each individual component of a satellite will be tested in the same way and tested again when all the components are integrated together. This particular satellite passed all of its testing and was successfully launched in April of 2023 on an 8-year journey out to Jupiter. Okay, so now we've tested our satellite and we're ready for launch. In the final module of this course, we will wrap up and summarize what we've covered by walking through a handful of completed satellite missions.